Okay, we are now on to our next topic, which is called special transformations. So up to now, all the properties of transformations were general. Now we are going to talk about three special transformations. One is called an orthogonal transformation. The other one is called a dilatational transformation. The third one is called a symmetric transformation. Transformations can be identified by which vectors become the min-max vectors and how much they are stretched and rotated or inverted. Notice that you can talk about the transformation in terms of the min-max vectors alone. So it is extremely useful. The min-max vectors, the green vectors. Okay, so you can see how much the min-max vector translated. Can you see it became longer and it rotated. Let's play that again. So look at this side. Can you see that you can see how much it got stretched? And this side, if you see, you can see how much it got rotated. Can you see? How much it got longer or shorter, how much it got stretched, and how much it got rotated. Observe the green min-max vectors. They seem to do the same thing as the red vectors, but they actually rotate. The red vectors don't. So you can see that red vector also gets stretched, but the red vectors don't get rotated. The other thing is the red vectors don't get stretched as much as the green vectors. Can you see that? The green vectors get more because, of course, they are the principal axis, that is the major and minor axis. So dilatation is pure scaling, no rotations, no special maximum or minimum direction. Just scale up everything. Every direction just gets stretched out. Nothing else happens. There you go. Everything is a min-max vector. Everything is an eigenvector for this. So red could be, the red lines could be anywhere you like. The green lines could be anywhere you like. They're all the same. Simply scales all the vectors without rotating them. Every vector is an eigenvector, which means that they're not rotated. Every vector is a min-max vector, which means that they point in the direction of maximum stretch or minimum stretch. That is, they point in the direction of the major and minor axis. For a circle, of course, there is no major or no minor axis. Symmetric transformation, the orientation of the min-max vectors are unchanged. They represent pure shape change. So for in a symmetric transformation, the min-max vectors and eigenvectors are the same. So if you're used to making dough, I mean, whether you make a tortilla or a chapati or something, then you know what this means. If you look at the you can view this as elongation or compression along the min-max vector lines. That is what is happening. Stretch means elongation over compression. Vector rotations are symmetric about the special vectors. So let's see what I mean. So first, can you see it gets stretched this way? So there you go. Can you see how it gets stretched? And if I blow it up, you will see that all the other vectors are rotating symmetrically towards the min-max vector or away from the minor axis and towards the major axis. Can you see that? So vectors will rotate towards the major axis and away from the minor axis. That's what is happening. So this is referred to also as a pure stretch transformation. So it will have non-rotating maximum and minimum vectors. That is the geometric intuition. Orthogonal transformation is the opposite of this. Pure change of orientation. This is rotation or inversion, no shape change, no stretching, but there is rotation. So it should not say or rotation, it should just say no stretching, only rotation. All distances and angles are preserved. Notice the mirror image that occurred. I don't know whether you were able to see that. See, that's one of the things that you cannot show by smooth transformation. It just abruptly happens. So there is a change in handedness. What is counterclockwise initially may become clockwise afterwards. So that is, so in that sense, angles are not exactly preserved. They can be changed inside. So watch. Is it obvious to you that you saw the flip of the red and green arrows? Pay attention to the red and green arrows. You will see the flip. Did you see that? There. That's an orthogonal transformation. It's called proper orthogonal if there is no flip. There. And notice that there is no eigenvector for this setup at all, at least in 2 dimensions. In 3D, yes, it may. So that's where we have to think about all these things in different dimensions differently. So we are done. Our next topic is decomposition into simpler transformations, and we will talk about that later.